Good morning. Welcome to a new lecture in detection, and in this lecture we will be talking about performance of non-coherent systems. Okay. So, up to now what we have done is we have understood these coherent systems. So, in coherent systems the receiver has complete knowledge about the frequency and phase of the carrier, and what it does basically, it computes the real part of inner product of the received signal with the signal from the signal set. Okay. So, if I assume that there is no noise, so the received signal is exactly same as one of the signal from the signal set, then what it does is it takes the inner product of the signal with itself and it takes the real part of this inner product. Okay. Inner product of the signal with itself simply gives us the norm square of the signal, and norm square is anyway a real quantity. So, this is simply norm square of the signal. So, basically in the coherent receiver these operations are carried out. Let us see what happens in non-coherent receiver if these operations are carried out. So, here the received signal might be at certain phase offset than the signal from the signal set. Okay. So, let us assume that this is the signal from the signal set, this is the received signal, and the received signal is offset by this phase of theta from the signal in the signal set. When we take the inner product of this, so inner product of u with u e to the power j theta is simply inner product of u with u multiplied by e to the power minus j theta. Okay. We have seen in the first week itself that this inner product is an Hermitian bilinear operation. Okay. So, we know that this is norm square of u multiplied by e to the power minus j theta, and then if I take the real part of this, I simply get norm square of u multiplied by cos theta. And now theta can be anything, and if to make our life worse, if this theta is 90 degree, then r is 0 and hence everything is lost, and thus performance of a receiver degrades when there is certain phase offset. Okay. Frequency offsets also results in phase offsets in some sense. Okay. Hence, what we do in this non-coherent receiver, we change our strategy, and instead of taking the real part of inner product of signal with the received signal, what we do is we take the mod of this inner product, and now you see that this problem is sorted out. So, if we take the mod of this thing instead of taking the real part of this thing, what we will receive is simply norm square of signal. Okay. And thus, in absence of noise, this receiver works in the same way as the coherent receiver. There is no degradation, right. We will see now in this lecture what happens in the presence of noise. But overall what we are pointing out is, if you use the same strategy as we used in the coherent receiver, and if there is a certain phase offset, then the real part of inner product of signal with the received signal might give you a flat 0. And thus, in case of non-coherent receiver, what we do is we take the mod of inner product of the signal with the received signal. Okay. And so far it seems that it works fine. Let us look at the receiver for a non-coherent system, and we are not showing this part because this part remains exactly as for the coherent receiver, but then you do certain operations once you have received the cosine and sine part using the techniques that you used in the coherent receivers. Namely, you have a multiplier which shifts down the received signal to baseband signal. You will have a low pass filter, you will have a matched filter and a sampler. Okay. Everything remains same in the front end of this receiver. Okay. So, what we receive in this non-coherent receiver is UC cap and US cap, and what's this UC cap and US cap? These are the cosine and sine parts of the received baseband signal in the presence of frequency and phase offset. So, if I assume that my received baseband signal will be simply u multiplied by e to the power j theta, and from this I can get the cosine and sine part that I have in here. Okay. U is simply uc plus j us. So, these are the cosine and sine parts that we intend to receive, but then this thing in the presence of frequency and phase offset gets multiplied by this factor. And just working out the arithmetic, you can see that this UC cap is UC cos theta minus US sin theta, and US cap is UC sin theta plus US cos theta. Actually, this we have derived in one of the previous lectures in modulation, and hence I am not repeating it. Okay. I am sort of revising the stuff for you. Okay. So, what you do is you square this thing in here and you square this thing and you add these two components and then you take the square root. Okay. Why are we taking the square root? Anyway, it is a deterministic function, and we have seen in detection already by reading this theorem of reversibility, which states that any deterministic function does not change or alter probability of error. Thus, if you have it or you do not have it, does not do anything to probability of error, but it lets us have nice PDFs, which we will see, and that is why we are having this square root function. Okay. Anyway, so you can see easily that if you square this UC cap and you square this US cap and you add these two things up, what you simply get is norm square of u, and that is what we wanted. Once you take the square root of this norm square of u, you get norm of u, easy. Okay. So, in non-coherent systems we add this thing up here and we can detect again the signals. So far so good. What happens to this noise? So, if we assume that there is a noise depicted by a random variable NC in the cosine part or in the in phase channel, and let us assume that there is a noise depicted by this random variable Ns in this Q channel or in the sine part, then what happens is when you have this operation of squaring in phase and Q phase component, adding them up and then taking the square root of this, you also do this with noise. So, at the end of the system you have got a noise random variable n, which is square root of nc square plus ns square, and of course, these random variables are independent of each other. They are Gaussian with 0 mean and certain variance we can assume to be n naught by 2. And the first question that we like to ask is what is the distribution of this n, okay? And that we will see. Okay. So, let us do one quick exercise from random variables and processes word, and let us say we have two random variables x and y. These random variables are independent of each other. Let us assume that these random variables are Gaussian with 0 mean and variance of sigma square, and what we want is we want to find out the distribution of this r and phi. These random variables are described by these relationships. And if you look at these two equations, you know what I am trying to do. I am trying to change my coordinate system from Cartesian coordinate system to polar coordinate system. Okay. And I want to understand what is the joint PDF of this random variable r and phi. Okay. That is what we are up to. And the first thing that we have to start with is writing the joint PDF of these random variables x and y. And if these random variables are independent, the joint PDF is simply obtained by multiplying the marginal PDF. Marginal PDF of this random variable x is this, marginal PDF of random variable y is this. They are Gaussian with 0 mean and variance of sigma square. So, you multiply these two PDF and you get this PDF. This we have also seen when we have discussed proper complex Gaussian random variables. Okay. So, we have been able to define the joint PDF of these random variables x and y, and now we have to think about the PDF of these random variables r and phi. Now, what you can see easily is that when you go from one coordinate system to another coordinate system, the probability of finding a point in this coordinate system, let us say in the space dx dy, would be same as the probability of finding the map of the points in this space in the space dr d phi. Okay. That means what I am simply saying is, if I have a space, if this space gets mapped to a different space in another coordinate system, the probability of finding a point in this space will be same as probability of finding a point in this space. So, probability remain conserved, and this is the probability of finding a point in dr d phi space, this is the probability of finding the point in dx dy space. And the first thing that you must have learned when you have learned about interchanging the coordinate systems is this relationship between Cartesian coordinates and polar coordinates. You must have seen that dx dy in polar coordinates is r dr d phi. Okay. And you must have seen this picture as well. It is very easy picture to remember this. So, if you take an incremental length of dr, and if you take this is r d phi, then you know that this space corresponds to space dx dy, and hence r dr d phi is simply dx dy. This is all what you need to find out the PDF or joint PDF of r and phi if you know the joint PDF of x and y. So, what we do here is we have already known this. So, we have substituted joint PDF of x and y, which is this, that was in the form of, let me look at this again, and x square plus y square is simply r square. So, if you see, this is simply this. Okay. Now, I think we do not need it, and what we have done more is we have replaced this dx dy with r dr d phi, and now we have got this expression. From this, what we get is the joint PDF of r and phi is simply this function. If you look at this function for 30 seconds or 1 minute, what you will realize is that this function is not a function of phi, it is just a function of r. and thus phi must be uniformly distributed random variable. That means it should have same distribution for all angles. If that was not the case, then the joint PDF must be a function of phi, which it is not, and thus if you look at this PDF or joint PDF, you can realize that phi must be uniformly distributed random variable. And now the next job is to find out the marginal PDF of this random variable R. How do we go from joint PDF to marginal PDF? This is straightforward. You take the joint PDF and you integrate it with respect to one random variable. So, you integrate this with respect to d phi, and that will kill out this phi from this joint PDF, and you get the marginal PDF for R. Easy. So, integrating this will let you have the marginal PDF of random variable R, which is this function. Note that this R must be strictly positive, because finally you are having R as square root of x square plus y square, which is a positive quantity. Okay. And what will be the PDF of phi? It is a uniformly distributed random variable between 0 to 2 pi. So, the marginal PDF of phi should be 1 by 2 pi for phi between 0 and 2 pi. Okay. If you multiply these two PDFs, you can see that the product of this PDF is simply the joint PDF of these two random variables, and this is a quick proof that these R and phi are independent of each other. So, we have learned a lot of stuff here. What we have started with, we have started with two random variables x and y, and we want to derive the probability distribution function of two another random variables r and phi. R is square root of x square plus y square, and phi is tan inverse of y by x. Doing some arithmetic, we have derived the joint PDF of R and phi. From that, we have got the marginal PDF of these two random variables, and we have also made a quick proof that these random variables are independent. So, it is the time now to look at this equation little harder, and I have got a figure for that. So, here I am plotting the marginal PDF of this random variable R, and this PDF has also got the name because of its applications to various fields. It is used in non-coherent detection, it is also used in wireless communication. You model the wireless channel as Rayleigh channel. Okay. It is very useful probability density function. It looks like this. It is not symmetric PDF. The numerical values of R are only positive numbers. So, unlike Gaussian, which runs from minus infinity to plus infinity, it does not run from minus infinity to plus infinity, but it goes from 0 to plus infinity. It is not at all a symmetric PDF. The mean of this PDF is sigma times the square root of pi by 2, and the variance of this PDF is 2 minus pi by 2 multiplied by sigma square. So, you might have to use this sometimes in your life, and thus it is a good idea to know that these mean and variances exist. Okay. Now, from this knowledge of Rayleigh PDF, we can start looking into the question of how can I do detection in these non-coherent systems, and we start with this OK system, on off keying. Okay. It is a binary PAM. All right. So, now in OK we are having just one real number. So, u in general is uc plus jus, and you do not have this thing in here if you are just using one real dimension. So, u is simply uc, and what is this uc cap? Uc cap is uc cos theta and us cap is uc sin theta. That means, after this match filter and the sampler, we are going to get uc cos theta in this I channel or x channel or cosine channel, there are various names for the same thing, and I also use them interchangeably to confuse you, and thus it is good idea to get accustomed to all these words. In this y channel or q channel or sine channel, what we get is uc sin theta, and the first question that we like to ask is, what is the probability density function of this random variables x and y? Of course, there must be some noise hitting this receiver somewhere, and this will be a Gaussian noise as usual. So, what we will believe is that there is a Gaussian noise riding on this signal, and let us try to see what is the PDF of x and y, and from that we will be investigating what is the PDF of the square root of x square plus y square. That is the big plan. So, what is the PDF of x? X being Gaussian, things are simple. Just now the mean shifts to u cos theta, and what is the PDF of y? Again it is Gaussian, is simple, the mean here is u sin theta, and we assume that the variance of the noise is sigma square. Now, from these x and y's, what we are interested in finding is r, which is the square root of x square plus y square, and thus we can use the same strategy as we used in this lecture while deriving Rayleigh PDF. So, I want to equate the probabilities in the two words, in Cartesian coordinate and in polar coordinate, and then I will like to substitute the joint PDF of x and y, substitute the fact that dx dy is r dr d phi, and from that I hope to get this joint PDF of r and phi. So, the joint PDF of r and phi, by using the same thing that we have just done, can be obtained like this. In the previous example I just had x square plus y square, and here because there is a signal also present in these two branches, I have these factors popping up, that is the only difference, everything else remains same. And it does not take more than high school trigonometry to work out these identities. So, we have to expand this, and you just have to use a square plus b square plus 2ab identity, which even I can remember. So, expanding on this, I get x square plus u square cos square theta minus 2 x u cos theta. Expanding on this, I get y square plus u square sin square theta minus 2 y u sin theta. Then I add these terms, I get x square plus y square. I can combine these two terms into u square, and I get these two terms here. Okay. And then I use the fact that x square plus y square is r square and tan phi is y by x. So, these are the numerical values of the random variables. If random variables are related by this expression, their numerical values should also be related by a similar expression. Okay. And from this I get x is r cos phi and y is r sin phi from these two basic equations. So, while trying to solve for this, I can substitute x here as r cos phi, this y here as r sin phi. I can substitute r square in place of x square plus y square. So, I get r square plus u square minus 2 r cos phi u cos theta minus 2 r sin phi u sin theta, and I can combine this term like this. Okay. That is it, not hard. Now, I have to substitute this in that argument and divide this by 2 sigma square, and then same as before, to get the marginal PDF from this joint PDF, I have to take this joint PDF and I have to integrate with respect to phi if I have to find out the marginal PDF of random variable r. And what you can do is you can collect the terms which are independent of this phi. So, I have this two terms which are independent of phi. I can take this out of the integration because they are constants with respect to phi. So, I have this function and I have this integration to solve. Solving this integration in the first sight looks scary, but actually it is not, and as an engineer you must know how to deal with such functions because you must have seen them several times. For example, whenever you have cylindrical geometries or polar coordinates, we mostly get to these kind of functions. You must have seen these functions in waveguides or in optical fiber. Okay. So, we know how to solve this if you think little bit, and if you have done a course in electromagnetism where you have seen these waveguides or optical fibers. This is actually a modified Bessel function of first kind in 0 order, simple. So, I can replace this integration by this modified Bessel function of first kind in 0 order, or modified 0 order Bessel function of first kind, howsoever you like to call that, does not matter. And this is simply I naught u r by sigma square, and thus I can get the marginal PDF of this random variable r. So, it is like some maths involved here. So, let us look at this modified 0 order Bessel function of first kind. It is defined as 1 by 2 pi multiplied by the integration of e to the power x cos phi in the limits 0 to 2 pi. Okay. This is the definition of this modified 0 order Bessel function of first kind. The integration that we were dealing with was this, and there was also 1 by 2 pi here. So, we were dealing with this. So, you can easily appreciate that this thing is x. Okay. What we have here, which is different from this basic definition, that we have cos of phi minus theta instead of simply cos phi, but that is not a problem because cos is a periodic function, and if you integrate a periodic function in one period, then the initial phase from where you start does not matter. This theta simply shifts the phase of this function, but being a periodic function, the initial phase does not matter if you are carrying out the integration over one time period, is not it? So, this integration is same as carrying out this integration, and this is simply I naught of u r divided by sigma square. Okay. So, do not get confused. So, what we have got is the marginal PDF of random variable r is this. Does it have a popular name? Yes, it does. It is known as Rayleigh PDF, named after the famous engineer Rayleigh. So, Rayleigh PDF looks like this. So, it contains this modified 0 order Bessel function of first kind. Okay. We will try to look this Rayleigh PDF again, but let us first ask some basic questions. What is this I naught of 0? If you have to investigate this at 0, e to the power 0 is 1. So, here we just have 1 and this will be 1. So, I naught of 0 is 1. And if in this PDF if you have u as 0, what do we get? So, if you substitute u as 0, this term vanishes. So, you simply have e to the power minus r square by 2 sigma square multiplied by I naught 0, because u is 0 and this is 1, right. So, this converts to Rayleigh PDF and this was bound to happen, because what was the difference between Rayleigh PDF and Rayleigh PDF? When we derived this Rayleigh PDF, we just assumed that there is a noise, there was no signal riding on the noise, and when we have done the derivation for Rayleigh PDF, the thing that changed here is now we have signal plus noise hitting the block which is carrying out first the square of the terms, summing them up and then taking the square root operation. Okay. So, the basic difference between the Rayleigh PDF and the Rayleigh PDF is we get Rayleigh PDF when we just assume that there is a noise hitting us in the I and Q channel, and we get this Rayleigh PDF when there is a signal riding along with noise. Okay. So, that is the main difference. Let us see how this modified 0 order Bessel function of first kind looks like. It is a monotonically increasing function of x. So, that is nice, and like we have this normal random variables, we also have a standardized form of Rayleigh density functions. Okay. The standardized form of Rayleigh density function is this. So, it is very similar to the density function that we have, but this is a standardized Rayleigh density function. What you can see is if you change this lambda in here, so you can think about this lambda as u that we have in our density function, and you can think about this z as r that we had in our density function, and variance is assumed to be 1 in this case. Okay. So, what you can see is if you change this lambda, that means it is akin to increasing the signal power that is riding along with the noise, you get to different Rayleigh density functions. So, when there is no signal power, then you get a Rayleigh PDF. As you increase the signal power, lambda increases and you get other density functions. If your lambda is pretty large, then the Rayleigh density function begins to become like a Gaussian density function. So, it is like Gaussian density function, it will never become a Gaussian density function, because Gaussian density function runs from minus infinity to plus infinity, and this Rayleigh density function runs only over positive arguments. So, in no sense it will be a Gaussian density function, but it will become like Gaussian density function. So, when the tail of this Gaussian density function does not matter, then you can very well approximate it as a Gaussian function, okay, and that happens when your signal power is large. We have a mathematical kind of proof for this. So, this modified Bessel function of the first kind can be approximated like this. Do not ask me for the proof of this, this is a well established relationship which I am just using. And if my modified Bessel function can be approximated like this for large u or signal power, then the Rayleigh density function that I had before, you can substitute this approximation of this Bessel function in this density function. Okay. So, you are just substituting this thing in place of this in here. What will I get? So, I will get this term which is here, then I have got this scaling factor in here. So, I am replacing this term with these two newly added terms. So, one is this term and one is this factor. And then I can multiply this with 2, and I can try to combine this with this, and my resultant density function begins to look like this. And then again using this identity of a minus b whole square, I can reduce this to this. So, if I look at R around u, this factor becomes 1 and this thing can be approximated as this thing. So, it begins to behave like a Gaussian density function in approximation, and that is one nice thing that we have in here. So, we can assume that our abnose is large. When my abnose is large, instead of thinking in terms of Richian density function, I can think in terms of Gaussian density function and I can do quick calculations. Okay? So, that is the strategy that we have in here. So, after completing this derivation of Richian PDF and Rayleigh PDF, we are good to go and derive the performance of non-coherent OK system. And what we are assuming is that when we have this hypothesis 1, we are transmitting a signal u, and when we have this hypothesis 0, we transmit 0. Okay. So, the PDF when 1 is transmitted, that means you have the noise riding with the signal, would be a Richian PDF, and this will be the expression of that PDF. We have derived this. And the probability density when you are transmitting 0 will be a Rayleigh probability density, because u is 0 here. Okay. So, what we have in here is we have different kinds of likelihoods when 1 is transmitted and when 0 is transmitted. Now, first thing that you have to identify is where is the threshold of detection. Okay. When will receiver will decide for 1 and when will it decide for 0. So, to think about that, we need to find out the threshold, and threshold is the place where these two likelihoods are same. Okay. Let me show that. So, we have to find out this threshold A naught, which you can simply find by comparing the likelihood when hypothesis 1 is transmitted with the likelihood when hypothesis 0 is transmitted. And can I make use of some simplifications here? So, this term will simply cancel out with, okay, and this will also cancel out. So, what you have is e to the power minus u square by 2 sigma square times this modified Bessel function must be 1. It is little bit tedious to compute a naught from here, but you can show that approximately a naught is given by this thing. Now, we use the properties that we have learned while covering this mesh filter, that if I use a mesh filter, which I will because it is the most optimum filter to use, my u is simply E s and my sigma square is n naught by 2 times E s, and this we have seen even in the last lecture. So, from this, the square of u by sigma is E s square divided by n naught E s by 2. So, I am simply substituting these numbers here, and from here you get that this is 4 E b by n naught. Remember, in OK systems E b is E s by 2. because for one bit I am transmitting Es energy and for the another bit I am transmitting 0 energy. Thus, on an average the energy per symbol is Es by 2 and bit energy is also the average symbol energy. Okay. Substituting in place of this, the value that we have derived for u by sigma square, the A naught that we get is this. Okay. And now the problem is, in this system and in any OOK system, whether it is a coherent OOK or non-coherent OOK, this is the problem that you have to live with in OOK system, that threshold is a function of EB by N naught. For example, if I would have used an antipodal system or an antipodal signaling scheme, where does the threshold lie? If the signals are of equal priors, then the threshold lies always at 0, there is no problem. But here in case of OK system, threshold depends upon EBNO. Okay. So, for example, if you have an OK system, so here is your signal 1, here is your signal 0, your threshold will lie in between these two signal points, and thus it depends upon with what energy you are transmitting 1. And because the energy that has a role in the receiver performance is the energy which receiver is actually receiving, and thus it depends upon several factors like how far the receiver is from the transmitter, what kind of channel is in between the transmitter and receiver, what fraction of the transmitted energy is reaching the receiver, what powers the transmitter is transmitting, and on several factors. Whereas, if I would have had used an antipodal scheme, my threshold always sits at 0 in spite of the channel conditions, and that is why it is very useful, because threshold detection in antipodal schemes is thus trivial, it is 0 always, whereas the threshold detection becomes a serious problem in case of unipolar signaling mechanisms like on off keying. Okay. So, that is why practically the receiver becomes complicated for OOK systems. So, threshold depends upon EBNO, and this is a serious problem, especially in fading channels. And what we will like to do is, we want to assume this EBNO is pretty large than 1, so that I can approximate the threshold to be just EB. So, we do set of approximations because we want to arrive at a simple formula for probability of symbol error rate. Now, we ask the question, what is the probability of error given that hypothesis is 0? So, when we have transmitted hypothesis 0, that means we are not transmitting anything. So, ideally I should get a 0, but because of this noise acting in here, I might get a certain number, a certain numerical value, and if this received number exceeds the threshold of EB, I create an error, because then my receiver will decide for 1. Okay. So, you can think it like this, that the perpendicular bisector sits at EB. So, if the received numerical value is more than EB, then my detector will go for hypothesis 1, which will be an incorrect choice. And thus, to find out the probability of error given that we have transmitted hypothesis 0 can be simply obtained by evaluating this PDF's integration in the limit EB to infinity. And one thing that you must be really comfortable with is integrating this function. As very simple, there is a trick here. If you have to integrate this, what you have to do is simply replace this R with EB. That is the final answer that you will get. Mostly in this non-coherent systems and in wireless communication, you end up with these kinds of integration. Okay. And here the trick that we use is simply replace R with EB, and you get this function where R is replaced with EB. For example, this integration is simply this. Now, putting for the sigma square is n naught by 2 times E s, and thus this is simply E b square by n naught times 2 E b, E s is 2 E b. So, 1 E b cancels with 1 E b. So, I get the probability of error given hypothesis 0 is transmitted as e to the power minus E b by 2 n naught. So, it is straightforward, not that complicated. Okay. So, now we have to find the probability of error given that we have transmitted hypothesis 1, and this can be simply obtained by integrating this PDF from minus infinity to E b. So, now you notice that we have Gaussian PDF instead of Rayleigh PDF, and we have done this because it makes our life simple, and we have seen that this will be the case when abno is pretty large. Then why not assume abno to be pretty large, because that will simplify the life of receiver and it will also simplify our life. Okay. So, we have just replaced the Rayleigh PDF with Gaussian PDF, and then we have to integrate this between minus infinity to E b. Then we can get the probability of error given hypothesis 1 is transmitted, and this is q of root of E b by n naught. Okay. Now, we make use of another approximation. So, we will do it later, we have not done it yet. Let us first see what is the probability of error. So, this is the probability of error given hypothesis 0 is transmitted. This is the probability of error given hypothesis 1 is transmitted. You add these two probability of errors and divide by 2 to take the average, and now we are using the approximation that q of x is 1 by root 2 pi x e to the power minus x square by 2. Why are we using this approximation instead of e to the power minus x square by 2 approximation, which we have used several times before? This approximation has to be used when you are finding the slope at which BR curves decreases, right. So, when you are looking to think about numbers, how this BR decreases with abno. When you are trying to find out the exact value of the expression, then this is a better approximation to use. Okay. So, using this approximation for q of x, we can write this as this, and now you can see that if your abno is pretty large, then this term will have no contribution, it will be negligible, and thus my probability of error simply trims down to this value. So, this is the probability of error in non-coherent OOK systems, and we have seen in one of the lecture that probability of error in coherent systems is this, and there is not much to take between non-coherent and coherent OOK system probability of error. They look exactly similar, especially at large abnos. Okay. Now, let us quickly derive the probability of error in the case of binary frequency shift keying. So, in binary FSK you have two real dimensions to worry about. You can think of it as the two OOK systems, non-coherent one in I channel, one in Q channel, and then you have a decision device which decides based on the fact whether the output of this OK system is larger or whether the output of this OK system is larger. For example, if this OK system is in the I channel and this OK system is in the Q channel, and if here the output is larger, then the detector knows that this symbol must have been transmitted, or at least it guesses so. Okay. So, now let us assume that hypothesis 1 is transmitted, and let us assume that this is the signal corresponding to hypothesis 1. That means, we are assuming that we have a higher output in the I channel. This is the likelihood of the random variable available at the output of the I channel if hypothesis 1 is transmitted. This is the probability density function of the random variable at the output of the Q channel if hypothesis 1 is transmitted. Namely, here we will have a Rayleigh PDF because the signal rides on noise, and here we simply have Rayleigh PDF because there is no signal in the Q channel. Now, when will there be an error? There will be an error if the numerical value of this random variable exceeds the numerical value of this random variable, because then the detector will decide that hypothesis 0 is transmitted because the output of the Q channel is larger than the output of the I channel. That is so simple. So, there will be an error if hypothesis 1 is transmitted if the numerical value of the random variable corresponding to the Q channel exceeds the numerical value of the random variable corresponding to the I channel. Okay. Then what we have to do is we have to simply write down the joint PDF and we have to carry out this integration. So, R 1 can take any value between 0 to infinity, and if R naught takes a value between R 1 and infinity, of course, there is an error. Remember that these two random variables are independent of each other, and thus the joint PDF can be written as the product of the marginal PDFs, which we do in here. So, I have taken the PDF of this random variable R I, and I have taken the PDF of this random variable R Q. I have multiplied these two things, and now I want to compute this integration. Okay. And using the trick that I have introduced, that once you want to integrate this function, the output is simply this thing, and you have to replace this R naught with R 1, and you are done. Okay. So, that is it what we have. We have this function which remains exactly like this, we have this function which remains like this. And now, when you are thinking about integrating this function will be replaced. So, this function with dr naught will simply be replaced by e to the power minus r 1 square by 2 sigma square. Okay. So, that is what we do in here, we have this function. Okay. Now, we make some trivial changes in variables. We assume that x is root 2 r 1, alpha is u by root 2, and then first we identify which terms in here are independent of r 1. We have this term independent of r 1, we shift this out of this integration, and then we get this function remaining to be integrated. And if you look at for 10 seconds, you would be surprised that this is a very simple integration, because this is formula of Rayleigh PDF, and if you integrate any PDF between minus infinity to plus infinity, you get 1. But for Rayleigh and Rayleigh PDF, because they can only take positive arguments, if you integrate this from 0 to infinity, this should be 1, because it is a probability density function, and thus we easily get rid of this integration and we simply get 1. Okay. So, my probability of error given hypothesis 1 is transmitted is this, and now I replace the values of u and sigma, so that I get my answer in terms of abno. So, u square by 4 sigma square is 1 by 4 Es square, because u is Es, sigma square we know that it is n naught by 2 Es. So, we get Es by 2 n naught, and Es is Eb in case of frequency shift keying, because every signal has Es energy, average energy is also Es, and there is 1 bit per signal. So, Es is simply Eb. So, probability of error given hypothesis 1 is transmitted is this, okay, because u square by 4 sigma square is abno by 2. and this corresponds to overall probability of error, because we have seen this thing several times, because all signals are of equal energy, they are at same distances from each other, thus the probability of these signals hit will be uniform, and thus the average probability of error is simply the probability of error when one hypothesis is transmitted. Okay. I will not belabor it any longer. All right. So, probability of error in case of both non-coherent FSK and OK systems turned out to be same, and that was also the case in coherent FSK and OK systems. The probability of error was same. Now, let us look at the last stuff, one of the last, two more things to go, and one thing is thinking about this differential PSK systems, because they also sit in this non-coherent systems. Well, when you are talking about the phase, you can get confused that, for example, if my phase is 180° far, and if I have to receive this 1 and minus 1, and if there is a squaring operation, how would I be able to distinguish between these two signals? So, differential PSK, when we say that it is a non-coherent system, I simply mean that this does not require a carrier, because it uses the previous bit as the carrier. So, you know, in differential phase shift keying, one of the pulses is delayed, and this pulse, delayed pulse, acts as a carrier for the incoming pulse, because in differential phase shift keying we are rather worrying about finding out what is the difference in the phase between the present symbol and the past symbol. And so, we use the previous pulse as the carrier for the incoming pulse, okay. And that is why you do not use any carrier, but you draw your own carrier from the signal. So, that is the point, that is why we call this as belonging to family of non-coherent systems. This idea also we introduced before, that DPSK is actually an example of orthogonal modulation scheme. So, it should not be surprising that it should have the same error performance as we got for FSK, but with one small difference. So, in these orthogonal signals, two signals that we have in DPSK, so refer to lecture on differential modulation scheme if you have forgotten this, that we have these two orthogonal signals in DPSK. One, let us say, is u, one is u minus u, these signals are orthogonal. And what is the energy of each signal? Energy of each signal is 2 times energy of u. And what is the energy of u? Energy of u is same as the energy of bit. Thus, in DPSK, energy per signal is 2 times energy per bit, and that is why it gets a 3 dB improvement compared to FSK. In FSK, ES was simply EB. Here ES is 2 times EB, because in one signal you are having 2 bits, and that is why this probability of error improves by a factor of 3 dB. So, you do not have this 2 that you had in FSK system, that gets killed because of this fact. Simple. Now, the last point of this lecture, how can I think about this non-coherent multi-level frequency shift keying? Why we are just talking about this multi-level FSK and not about other modulation schemes, because practically this is the most used modulation scheme. Okay. Coherent FSK systems had certain problem, because you have to track frequency and phase, and thus when we want to use a large number of carriers, it is okay to live with a non-coherent system if it does not give a serious degradation in performance. Deriving the probability of error in this case is little bit tedious, but conceptually it is same. So, idea is exactly what we used in the case of deriving the probability of error in case of coherent FSK. So, remember, we had this bunch of random variables, and we said that the probability of being correct is when the numerical value of the random variable corresponding to the first hypothesis is maximum, then you are detecting the correct hypothesis. So, the probability of being correct is that the probability of the numerical value of the first random variable should be largest, and we state that thing in here. So, if the numerical value of the first random variable is R1, the numerical values of all other random variables should be smaller than R1. That is it conceptually, and then you write what is the probability of the first random variable picking up on a value around R1, which is this one. So, use the PDF of this random variable R1, multiply this with dR1 to find out what is the probability of this random variable sticking on a value around R1, and then you find out what is the probability of all these random variables taking a value less than R1. So, you pick on the probability density function of one random variable, which is Rayleigh. If you want to find out what is the probability of this random variable taking a value less than R1, you integrate this PDF from 0 to R1, and because we have m minus 1 terms in here, we multiply this with m minus 1 times and we integrate the whole thing. You can easily do this in MATLAB and can arrive at the expression of probability of being correct, which someone has done for us and solved it. So, probability of being correct, you can prove, turns out to be this. Of course, it is a very cumbersome formula which I will not advise you to remember, but one thing and one message that you can draw from here is, if you work this out, you will see that the probability of error in non-coherent multi-level frequency shift keying systems is very close to that of multi-level coherent frequency shift keying systems, and this practically is very useful, because now you do not have to track the phase in frequency of m carriers if m is pretty large. Okay. So, with this we have completed the discussion on non-coherent systems, and we will move to some other interesting stuff in next lecture. Thank you.